In the past lecture about power series, we wanted to find the function f of x which gives the sum of a convergent power series. In this lecture, we define a power series associated with a given expression g of x under certain conditions on g of x. This power series representation is called a Taylor series of g of x. A Taylor series is a clever way to approximate a function using partial sum of terms that are expressed in terms of the function's derivatives at a single point. Maclaurin series, on the other hand, is a special type of Taylor series where the function's derivatives are taken as zero. Let's begin. Suppose that the function f has a power series centered at a, where Cn is a constant for all n. Also, define f0 to be the function f itself. Let's now observe the derivatives of f of x. So, taking the first derivative of f with respect to x, in this equation, we get the summation from n equals 1 to infinity of n times c sub n times x minus a raised to n minus 1. Now, f2, or the second derivative of f with respect to x, is equal to the derivative of f prime of x, which is the summation from n equals 2 to positive infinity of n times the exponent n minus 1 times c sub n times x minus a raised to n minus 2. Now, for f3, or the third derivative of f with respect to x, this is the derivative of f double prime, which gives us the summation from n equals 3 of n times n minus 1 times n minus 2 times c sub n times x minus a raised to n minus 3. So, keeping up with this pattern, let's now have the kth derivative of f with respect to x, or the summation from n equals k to positive infinity of, so we have n times n minus 1 times n minus 2 times n minus 3 and so on until n minus k plus 1, and then times c sub n times x minus a raised to n minus k. Okay? So, in particular, for any natural number k, we have the following expression for the kth derivative of f evaluated at a. So, this is because for n equals k, this becomes k times k minus 1 up to 1, or k factorial times c sub n. Okay, so k factorial times c sub k, and then x minus a raised to 0 or 1. That's why we have k factorial c sub k. Notice that when n equals k plus 1, then this is k plus 1 times k up to k plus 1 minus k plus 1, or 2, times c sub k plus 1, and then this becomes x minus a raised to 1. And if we evaluate fk of x at x equals a, this becomes 0. So the rest of the terms of this function is equal to 0, except for the first term where n equals k. Okay, so we obtain this expression for the kth derivative of f at x equals a. So solving for c sub k, we will get the kth derivative of f at a over k factorial. So we have shown that fk of a exists for all k in n, and the coefficients of the power series representation of f about a are of the following form. So this leads us to the following theorem. Okay. So suppose that the function f has a power series representation about the number a in the domain of f. Then the derivatives of f of all orders exist at A. So this is very important, the existence of the derivatives of f of all orders, okay, exists at A. And f of x is equal to the following power series. A summation from n equals 0 to infinity, and then c sub k has the form fk of a or fn of a over n factorial times x minus a to the n. And this is for all x in the interval of convergence of the series, where we define f0. Notice that we start here at n equals 0. So f0 is the function f itself. Okay, so this theorem tells us that if f has a power series representation, then this series is a Taylor series of f. So we can see in the following remarks. No? So for number 1, if the derivatives of f of all orders exist at A, we can associate to f this power series, where the coefficients are the derivatives of f at A, and this series is called the Taylor series for f about A. This series is named after the English mathematician Brooke Taylor, who introduced it in 1715. Okay, next. A special type of Taylor series, called the Maclaurin series, takes the derivatives at 0. Okay. This special case of Taylor series was named after Colin Maclaurin, a Scottish mathematician who extensively used this series in the 18th century. So we have this power series representation for f of x about 0, which is called the Maclaurin series for f. Now, in the last remark, it says that a function may not always be equal to its Taylor series at all points in the interval of convergence of the series. Let's have an example. Find the Taylor series for the expression 1 over x about 1 and find its interval of convergence. For the solution, let us first define f0 of x to be the function f of x, which is equal to the given expression 1 over x, which can be written as x to the negative 1. Now let us compute the derivatives of f of x. So observe that f prime of x is negative 1 times x to the negative 2. Now, f double prime of x is equal to, so this time this is positive 1 times 2, x to the negative 3. So differentiating this further, we get the third order derivative of f, which is equal to negative 1 times 2 times 3, x to the negative 4. So one more time, the fourth order derivative of f is equal to, so this time we have positive 1 times 2 times 3 times 4, x to the negative 5. Observe that the sign alternates and the coefficients are 1 factorial, 2 factorial, 3 factorial, and 4 factorial. Also, for the exponent of x, we have negative 2, negative 3, negative 4, and negative 5. So keeping up with this pattern, we say that the nth derivative of f is equal to negative 1 to the n, and then times n factorial x raised to the negative of n plus 1, where n is the order of the derivative of f. Now we want to find the Taylor series for 1 over x about 1. So we compute for fn of 1, which is equal to negative 1 to the n factorial, or as follows. Okay? And so the Taylor series for f of x about 1 is given by the following summation. So the summation from n equals 0 to positive infinity of the coefficient fn of 1 over n factorial times quantity x minus 1 to the n. So replacing fn of 1 by this expression, we get the summation of -1 to the n factorial over n factorial times x minus 1 to the n. So here we can cancel out the common factor n factorial, and so we have the summation from n equals 0 to positive infinity of -1 to the n x minus 1 to the n, or you can write this as quantity negative of x minus 1 to the n, which we know that this form follows a geometric series with common ratio negative of x minus 1. So recall that a geometric series is convergent if the absolute value of its common ratio is less than 1. So in this case, this geometric series is convergent if the absolute value of its common ratio, that is, the absolute value of x minus 1 is less than 1, and is divergent otherwise. So solving this inequality, okay, we get x minus 1 is between -1 and 1, or x is between 0 and 2. And so we say that the interval of convergence of this power series is the open interval 0, 2. Let's have another example. This time, let us find the Maclaurin series for the exponential of x and its interval of convergence. So for the solution, let f of x be the given expression e to the x. And note that the derivative of e to the x is e to the x itself. Then for any natural number n, we have the nth order derivative of f equals e to the x. Now, recall that the Maclaurin series is a Taylor series about 0. So solving this at x equals 0, we get fn of 0 equals e to the 0 or 1. So in particular, we have fn of 0 equals 1 for all natural number n. And so the coefficients of the Maclaurin series are of this form. Okay, so c sub n equals fn of 0 over n factorial, where the numerator is equal to 1 from what we obtained earlier, and then denominator is n factorial. And so the Maclaurin series for the exponential of x is given by the summation from n equals 0 to positive infinity of c sub n, which is 1 over n factorial, times the quantity x minus 0 to the n, or simply the summation from n equals 0 to infinity of x to the n over n factorial. So by ratio test, you can see that the interval of convergence of this series is the set of real numbers, where the complete solution can be seen in example 2.6.9 in the Math 22 module. In the previous example, we found the Maclaurin series for e to the x. This time, let's show that e to the x is equal to its Maclaurin series for all real number x. So for the proof, let's take this power series to be our h of x. Now, differentiating h with respect to x, we get h prime of x equals the summation from n equals 1 to positive infinity of n times x to the n minus 1 over n factorial. Now, we can cancel out the common factor n in the numerator and in the denominator, which gives us the summation from n equals 1 to positive infinity of x to the n minus 1 over quantity n minus 1 factorial. Now notice that when n equals 1, this gives us x to the 0 over 0 factorial, which is the same as taking the summation of x to the n over n factorial, where the summation starts from n equals 0. And this is precisely our h of x. So in this solution, we have shown that h prime of x equals h of x. And so, we say that h satisfies the differential equation h prime of x equals h of x. So from here, this implies that h of x is equal to the exponential of x times some constant c. So let's check. If we differentiate h of x, we get the same result, c e to the x. Now, to see how c e to the x is obtained, let us look at the following solution. So here, let's take y to be our h of x. Then, given y equals h of x and h prime of x equals h of x, we can write this as dy over dx equals y. Okay? Now, working with differentials, we can write this as dy over y equals dx. Now, taking the integral of both sides, on the left-hand side, we will get ln of y. On the right-hand side, we will get x plus some constant. Okay. Now, let's take this constant to be, say, ln of c. Okay. Then, we have ln y equals x plus ln c, or e raised to x plus ln c equals y. Okay? But e to the x plus ln c is equal to e to the x times c equals y. So therefore, we have shown that h of x is equal to the exponential of x times some constant c. Okay, so this must be x. Okay, so that's why we have h of x equals c times exponential of x for some constant c. Now, let's take x to be equal to 0. So this gives us h of 0 equals c e to the 0 or c, which is as follows. Okay. Now, on this part of the equality, note that we can expand this summation as follows. Okay. So this is equal to, so we start at n equals 0. So we have x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on, which is equal to x to the 0 over 0 factorial is 1 plus next term is x plus x squared over 2 plus x cubed over 6 and so on. Okay, so if we take this x to be equal to 0, so the terms here are all 0 and we are left with the first term 1. That's why this summation at x equals 0 is equal to 1. Okay, so here we have solved for the value of c, where c is equal to 1. And so, finally, we have h of x equals e to the x, and h of x equals this Maclaurin series. So finally, we have the exponential of x equal to this power series for all real number x. So this ends the proof for this example. Let's now use the result in the previous example to find the sum of the summation from n equals 1 to infinity of 1 over n factorial times n plus 2. The technique here is to consider the product x e to the x. Now, since e to the x is equal to this series, then x e to the x is equal to x times the series n equals 0 to infinity of x to the n over n factorial. So here we can incorporate x into this summation. So we can write the summation from n equals 0 to infinity of x to the n plus 1 over n factorial. Okay, so now for t greater than 0, we have the following definite integral for x e to the x, which we can solve by solving the integral of this series from 0 to t dx. Okay, so the integral of this summation is equal to the summation from 0 to infinity of x raised to n plus 2 over n factorial times n plus 2 evaluated from x equals 0 to x equals t. Now this gives us the summation from n equals 0 to infinity of t raised to n plus 2 over n factorial times n plus 2. Okay, so this result is almost similar now to the given summation in the problem. Okay, so here we can just take t equals 1 later. Okay, now on the other hand, we can solve the integral of x e to the x dx by using integration by parts. So doing so, we get the definite integral of x e to the x dx from 0 to t equals x e to the x minus e to the x evaluated from x equals 0 to t, which is equal to t e to the t minus e to the t plus 1. Since this summation is equal to the definite integral of x e to the x dx from 0 to t, which is also equal to this expression, then we can equate the two expressions as follows. Okay, so as I mentioned earlier, let's now take t equals 1. Doing so, we will get 0 minus 0 plus 1 on the left-hand side and summation from n equals 1 to infinity of 1 over n factorial times n plus 2 on the right-hand side. Now, this is now looking very similar to the given summation in the problem. However, in the given problem, the summation starts at n equals 1. In this case, we have the summation starting from n equals 0. What we can do here is to separate the term where n equals 0 from the rest of the terms of this summation. So note that when n is 0, we have 1 over 0 factorial times 0 plus 2 or 1/2 for the first term. And then for the rest of the terms, we have the summation from n equals 1 to infinity of this expression, 1 over n factorial times n plus 2. Okay? So solving for this summation, we get this summation equal to 1 minus 1/2 or 1/2. Let's now find the Maclaurin series for sine x. So to start, let f of x equals sine x. Now here we will need to find the derivative of all orders of sine x. So let's consider f0 of x, or f of x equals sine x. Okay, and then we have f prime of x equals cosine x. F double prime of x equals negative sine x. And then the third order derivative of f is equal to negative cosine x. Now differentiating this further, we obtain the fourth order derivative of f, which is equal to sine x. So now we're back at f0 of x. So notice that if I differentiate this further, we get the fifth order derivative of f, which is equal to cosine x. Okay, and you know the pattern, right? So observe that the derivatives of sine x repeat after a cycle of 4. Okay, and so for any natural number k, we have the following expressions for the nth order derivative of f of x. Okay, so here we have sine x if n, which is the order of the derivative, has the form 4k or is a multiple of 4. Okay, next, fn of x is equal to cosine x if the order of the derivative n is of the form 4k plus 1. And then we have negative sine x if n is of the form 4k plus 2. And finally, we have negative cosine x if n is of the form 4k plus 3. Okay, so now in particular, at the desired center of the power series, so note that we're dealing with Maclaurin series. So this is a Taylor series centered at 0. So let's look at the values of fn at 0. Okay, so note that fn of 0, so we have sine 0 is 0, cosine 0 is 1, negative sine 0 is 0, and negative cosine 0 is negative 1. So notice that we only have 3 values for fn of 0. They are 0, 1, and negative 1. And so we say that for fn of 0, we have, or this is equal to 1, if n is of the form 4k plus 1. Next, fn of 0 is equal to negative 1 if n is of the form 4k plus 3. And finally, fn of 0 is equal to 0 elsewhere or otherwise. Okay, and so the Maclaurin series for sine x is the summation from n equals 0 to infinity of fn of 0 over n factorial x to the n, which is equal to, okay, so starting from n equals 0, so we get fn of 0 equals 0. So this is 0 plus, so when n is 1, we get x over 1 factorial, and then plus 0 minus x cubed over 3 factorial, plus 0 plus x to the 5th over 5 factorial, plus 0 minus x to the 7 over 7 factorial, and so on. Notice the pattern that the sign is alternating for each term, and then the exponent of x corresponds to the value in the factorial in the denominator, and that the exponents and the factorials are all odd numbers. Okay, so we can write this in compact form as follows. So we have the summation from n equals 0 to infinity of negative 1 to the n, which makes this series alternating. Okay, and then x raised to 2n plus 1 over quantity 2n plus 1 factorial. So this expression in blue is the Maclaurin series for sine x. In the previous examples, we have obtained the Maclaurin series of the functions e to the x and sine x. This table shows the Maclaurin series of some common functions and their radius of convergence. The derivation of the Maclaurin series of the remaining functions is left as an exercise.